Welcome back to Mechanical Engineering Made Simple.
It's great to be back here.
Today, we're doing a deep dive into a scenario that is probably going to trigger some PTSD for a lot of you listening.
Oh yeah, I know exactly which scenario you're talking about.
The phantom failure. You know the one.
Oh,
You have a critical pump or a mixer in a plant. It's midnight, the machine goes down, maintenance tears it apart, finds a blown mechanical seal, replaces it, and, high fives everyone. Case closed.
until 2 weeks later when the exact same seal blows again.
Exactly. And that is where the finger pointing starts. The seal guy blames the installation guy blames the bearing, and the bearing guy blames the lubricant.
Always the lubricant.
Right. But today, we're going to look at the evidence provided in our source material and build a case against the suspect that usually walks away scot-free. The shaft. It's the literal backbone of the equipment, yet it's often the last thing checked. We're going to walk you through the physics of why this happens, moving past the basic torque calculations and getting into deflection, surface finish, and the human element of installation.
It's a classic case of looking at the symptom rather than the disease. You mentioned torque calculations, and that is usually where the trouble begins. We call this the trap of just enough.
Right, let's set the scene with the design phase. Let's say we have an engineer, we'll call him Bob. Bob is designing a mixer shaft. He looks at the horsepower, looks at the RPM, calculates the torque, and picks the diameter that guarantees the steel won't snap.
And on paper, Bob is a hero. The safety factor says the shaft allows for, say, 20,000 psi of shear stress, and he's only at 5,000. It's never going to break.
But then the machine is built, and the seal leaks immediately. Bob is completely confused because his math says the shaft is strong enough.
And he's right, it is strong enough, but he fell for the classic blunder. He assumed torque chooses the diameter. It doesn't. Constraints choose the diameter.
Specifically, stiffness constraints. This is the difference between will it break and will it bend.
Exactly. In the industry, we lovingly call it noodling. A shaft can be perfectly capable of transmitting the torque without snapping, but still act like a wet noodle under radial loads.
Like hydraulic forces?
Right, hydraulic forces or the weight of a massive impeller at the end of it.
It's intuitive when you think about it. Steel is strong, but it is also elastic. If you have a long, skinny shaft, it acts like a diving board.
That's a perfect analogy. And if that diving board bounces too much right where the mechanical seal is trying to do its job, you have a massive problem.
And this is where the source material gets very specific about limits. If that shaft deflects or bends even a tiny fraction of an inch right where it passes through the mechanical seal, you're in trouble.
Deep trouble. The seal faces are lapped flat to within light bands. We are talking microscopic flatness. If the shaft bends, it literally forces those faces to open up on one side.
Once they open, the fluid gets out. Or worse, abrasive particles get in.
The sources we looked at for mixer analysis are pretty strict here. For a general shaft, you might get away with a total centerline deflection of 125 thousandths of an inch. That's 0.125. That sounds small.
But for a mechanical seal?
It's an order of magnitude tighter. You generally cannot exceed 0.0015 inches at the seal face. That's 1.5 thousandths.
To put that in perspective for you, a human hair is about 3 thousandths. So we are talking about half the width of a human hair. If Bob's shaft bends the width of a single hair, his design has failed.
And the worst part, when the machine stops, the shaft springs back to perfectly straight. The mechanic pulls it out, puts a straight edge on it, and says the shaft is fine, but it was the murderer all along.
So Bob needs to stop calculating for stress and start calculating for deflection. He needs to beef up the diameter, not because the torque requires it, but because the seal requires it.
Precisely. Stiffness is the governing factor in 90% of rotating equipment design.
Okay, so let's say Bob fixes that. He makes the shaft thicker, it's stiff, doesn't noodle, but 6 months later, snap, a clean break. And it almost never breaks in the middle of a long, smooth section, does it?
Rarely. It almost always breaks at a transition, a shoulder, a keyway, a thread relief.
This brings us to the concept of stress risers. I always like the analogy of water flowing through a pipe for this.
It's the best way to visualize it, yeah.
If you have a smooth, straight pipe, the water flows logically. But if you have a sudden 90-degree turn or a sharp restriction, you get turbulence. You get pressure spikes right at that corner.
Stress acts the exact same way. It flows through the metal. If you force that stress to navigate a sharp 90-degree corner where a bearing sits, the stress piles up at that corner.
The technical term is stress concentration factors, or KT.
Right. And that factor can be huge. A sharp corner can multiply the local stress by a factor of 3 or 4. So Bob calculated 5,000 psi of stress, but at that tiny corner, it's actually 20,000 psi.
And that's exactly where the crack initiates. It's insidious because the rest of the shaft is barely working, but that one corner is screaming for help.
The fix is usually geometry. You need a fillet radius. You need a curve to guide that stress around the corner, just like a smooth bend in a pipe helps water flow.
Now, there's another geometry crime we need to discuss, and the machinery's handbook is pretty ruthless about this one. Keyways.
Ah, the necessary evil. We need keyways to transmit torque to the coupling or the impeller, but man, do they hurt the shaft.
The source material threw out a number that actually surprised me. It suggested that if you cut a standard keyway into a shaft, you should consider that shaft's strength effectiveness to be reduced to roughly 75% of a solid shaft.
It sounds high, but it makes total sense. You aren't just removing material, you are adding 2 sharp internal corners at the bottom of that groove. It's a double whammy of cross-section reduction and stress concentration.
So if you are designing right to the limit, and you forget to account for that 25% loss in capacity,
You are operating in the danger zone. And that's not even touching on the type of keyway. If you use a sled runner keyway versus an end mill keyway, the stress profiles change completely. But the main takeaway for you is never assume a keyed shaft has the same rating as the round bar it came from.
it effectively makes a 2-inch shaft behave like a 1.5-inch shaft in terms of fatigue limit.
That is a fair approximation, yes.
Okay, moving on. Let's assume the geometry is good, the shaft is stiff, the corners are radius, the keyway is accounted for. We move to the next layer of the onion, the mystery leak.
This is the one that drives maintenance guys completely crazy. You pull the shaft and it looks perfect. It's shiny, it's smooth, but oil keeps pouring past the lip seal.
And naturally, they replace the seal thinking they just got a dud.
Right. But this is where we have to look at the fishbone of failure, specifically the surface finish branch. You mentioned shiny. In the world of sealing, shiny can actually be a huge problem.
Because if it's too smooth, it can't hold lubrication.
Exactly. It's a Goldilocks situation. If the shaft is too rough, it acts like a file and grinds the seal lip down. If it's mirror polished, the seal runs dry, gets hot, and blisters. You need a specific roughness average, usually between 10 and 20 Ra, to hold just enough oil to keep the seal happy.
So it needs to be smooth, but not too smooth.
Okay, but what if the roughness is perfect?
Then we look for the invisible killer, machine lead.
This is a fascinating concept. I remember reading about this years ago and thinking it sounded like magic. Explain how a shaft can have a lead.
It comes down to how the shaft was ground at the factory. Imagine the grinding wheel touching the shaft. If that wheel moves laterally across the shaft while it's spinning, it leaves microscopic grooves,
Like the threads on a screw, but tiny.
invisible to the naked eye. But physics doesn't care if you can see them. If those microscopic threads are oriented in the wrong direction relative to the shaft rotation, they act like an Archimedes screw.
So the shaft is essentially a pump, a micropump. It actively pumps the oil under the seal lip and out into the world. You can have the tightest seal in the world, but if the shaft is pumping fluid past it, it's going to leak.
That is a nightmare to diagnose. How do you even prevent that?
You have to specify plunge grinding or ensure the polishing removes that directional lead. It's a detail that doesn't show up on a standard print, but it literally makes or breaks the machine.
It's wild to think that a microscopic groove can defeat a massive industrial pump.
It's the butterfly effect of engineering.
All right, let's talk timeline. We've covered immediate leaks, but what about the failure that happens 3 months down the road? The machine runs fine for a month, maybe 2, then suddenly snap.
This is fatigue, and this is why rotating equipment is so unforgiving compared to structural steel.
If you build a bridge, the beam just sits there. It holds the load.
Right, but a shaft is rotating. Think about a paper clip. You bend it once, it's fine. You bend it back, it's fine. You do that 50 times, and it snaps. That is fatigue failure.
And a rotating shaft is basically being bent back and forth thousands of times a minute.
Every single rotation. If there is a bending load, like from a heavy belt or a mixer impeller, the top of the shaft is in tension and the bottom is in compression. Half a turn later, that reverses. It's called fully reversed bending stress.
So even if the stress is well below the yield point, the point where it would permanently bend, it can still crack over time.
Correct. It's not a matter of if it fails, but when. Unless you design for infinite life. And that brings us to the sleep at night numbers.
I love that phrase, the sleep at night numbers.
Yeah.
Our source material, the analysis MW document, gives us some specific safety factors for this.
Right. It suggests that for the drive end, the end connected to the motor, you want a safety factor greater than 1.5.
1.5, that seems reasonable.
But for the stub end, the end inside the tank or the process, you want a safety factor greater than 2.0.
Why the difference? Why does the stub end need to be stronger?
Because the stub end is the Wild West. It's subjected to impact loads from the process, corrosion, weird hydraulics, maybe chunks of solid material hitting the impeller. It lives a much harder life. If you are designing under these numbers, you are rolling the dice.
So if Bob wants to sleep at night, he doubles the required strength on the wet end of the shaft.
Absolutely. It's cheap insurance compared to a catastrophic failure in the field.
We've covered the design, the geometry, the finish, and the fatigue. But we have to talk about the wild card, the variable that ruins even the best engineering, the human element.
Installation. This is where hearts are broken. You can do everything perfectly right in CAD, but if the person installing the bearing is having a bad day, it's game over.
The sources list a few common murder weapons here. The first one is the cocked bearing.
This is incredibly common. You're pressing a bearing onto a shaft, maybe it goes on a little crooked. Or, and this is very common, you're tightening the set screws on a lock nut.
And you just crank them down in a circle, right? 1, 2, 3, 4.
And that is exactly how you kill a bearing. If you tighten them in a circle, you tilt the lock nut. You have to use a star pattern, just like changing a tire on a car. If you don't, the inner ring of the bearing tilts relative to the shaft center line.
So it's not sitting flat.
Right. And as it spins, it creates a wobble. This leads to fretting corrosion, essentially microscopic rubbing between the shaft and the bearing.
That's where you see that reddish-brown dust when you take it apart.
Exactly. That's fretting corrosion. It's the blood spatter of a cocked bearing. Eventually, it loosens up, the shaft starts banging around, and you have a total failure.
Your bearing didn't fail, your installation did.
Exactly. Another one is cleanliness. If you mount a bearing over a burr or a tiny piece of dirt, you've created a stress riser and a misalignment before you even turn the switch on.
And there's this concept of creep from the SKF sources. This one sounds sinister.
Creep is what happens when you're too gentle. If you don't have a tight enough interference fit, a press fit on the ring that rotates, the friction isn't enough to hold it.
So the shaft turns, but the bearing ring slips.
It slips slowly. It creeps. And as it slips, it acts like a lathe, turning down the shaft diameter. I have seen shafts that were worn down by 1/2 inch because the bearing was spinning on the shaft instead of with the shaft.
Brutal. So the fit tolerance, getting that FN1 light drive fit or whatever this standard calls for, is absolutely critical.
It's not a suggestion, it's a requirement. If the ring rotates relative to the load, it must be an interference fit.
So look, we've dissected the crime scene. If we want to solve this, if you want to be the engineer that stops the cycle of failure, what are the golden rules?
It boils down to a philosophy change. First, stiffness over strength. Design for deflection first. If it's stiff enough for the seal, it's usually strong enough for the load.
Got it.
Second, soften the steps. Use generous fillets. Don't choke the stress flow. Third, respect the surface. No machine lead. And finally, verify the fit. Don't let a bad install ruin a good design.
Simple rules, but really hard to follow when you're under a tight deadline.
The laws of physics don't care about your deadline.
Well said. Now, before we wrap this investigation, we have to hit the mailbag. We pulled the most common Googled questions about shaft design to get some quick-fire answers. These are the things people are searching for but might be afraid to ask their senior engineers.
Let's hear them.
Question 1. Is a hollow shaft weaker than a solid shaft? Say Bob wants to save some money on shipping weight, but he's worried about strength.
The answer is surprisingly not much weaker. Think about where the stress is in torsion. It's on the outside skin of the shaft. The center of the shaft carries almost zero stress.
So the center is just dead weight.
Basically, it's just along for the ride. If you look at the math, torque capacity is a function of the outer diameter primarily. You can bore out the center, save significant mass and cost, and retain most of the torsional strength.
Are there downsides?
You have to be careful about wall thickness for buckling if the walls get too thin, but generally, hollow shafts are a great engineering trick. It's why drive shafts in cars are hollow.
Makes total sense. Question 2. Do I really need to balance a low-speed shaft? I mean, if it's only turning 100 RPM, does it even matter?
Yes, this is the low-speed myth. Even at 100 RPM, an unbalanced rotor creates centrifugal forces. Those forces hammer the bearings once per revolution.
It's like a slow heartbeat of destruction.
Exactly. It might not vibrate the floor like a high-speed turbine, but it is eating the fatigue life of your bearings. A family that solves together stays together, and balanced shafts keep the family of parts together.
I see what you did there. Question 3. My shaft is worn at the seal. There's a groove worn right into the metal. Do I have to scrap the whole thing and buy a new
Well,
shaft?
please don't. This is a great maintenance hack. You can
Yeah.
use a wear sleeve. Brands like SKF make these, they're often called speedy sleeves.
How do they work?
It's a super thin stainless steel sleeve. You press it right over the worn groove. It's so thin that you can usually use the exact same size seal over it. It gives you a brand new, perfect surface without machining and without scrapping the shaft.
That is a massive wallet saver right there,
Yeah,
especially if the shaft is custom or huge.
absolutely. It's a standard repair procedure in many plants.
Last question. What happens if I ignore the critical speed?
Catastrophe. Every shaft has a natural frequency, a speed where it naturally wants to vibrate like a guitar string. If you operate near this critical speed, the vibration becomes self-exciting. It feeds on itself
It just shakes itself apart.
violently.
Yeah.
You must ensure your operating speed is at least 20% away from that critical speed. You can be above it or below it, but do not hang out near it. It is a strict no-go zone.
So to recap our investigation today, the shaft is often the silent killer. It fails because of geometry, because it bends too much, or because we installed it wrong rarely, just because the torque was too high.
That's the ultimate takeaway. The best engineers don't just calculate, they inspect the install. They look at the whole picture, from the fillet radius to the guy tightening the set screws.
And here is a final provocative thought for you to chew on. With the rise of smart sensors and IoT in manufacturing, we're actually entering an era where you won't have to guess if a shaft is noodling or if a bearing is cocked. Imagine a future where the shaft itself tells you it's deflecting past that 0.0015-inch limit before the seal ever leaks. The days of the phantom failure might be numbered.
That is a future I'm looking forward to.
Me too. Well, if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.